of the sequence such that its distance from 3 is less than 1/10.
Yeah.
Okay, is that good enough?
No.
Is that good enough? If I just should happen to, suppose it should happen to dance up to 3, but then later on things go crazy. Jamie.
You also have to show that all terms after that are also within 1/10.
Yeah, I think the challenge is a little bit greater. I need to go out far enough such that beyond that point, all the terms of my sequence are guaranteed to be within 1/10 of 3. Are you following this? This is kind of complicated. Okay, so if she, by the way, so she's going to challenge me with 1/10. We call that tiny number, we call that epsilon. So she challenges me with an epsilon of 1/10. When she challenges me with that epsilon of 1/10, can you toss me a green marker from the table behind you? When she challenges me with an epsilon of 1/10, what she's basically saying is, I dare you to get within 1/10. 1 is fine. I don't need both of them. Thank you. Okay, so what we're doing is, we're basically saying, picture not to scale, we're basically saying, all right, let this be 3 plus a 10, let this be 3 minus a 10. She's daring me to get within 1/10. And what I must do, as Jamie said, and as some of you were also thinking, I need to go out far enough such that beyond that point I always remain within 1/10. In this number, which is the challenge that I meet, we call this, we use delta for this. My deltas are sometimes a little funny. But so by the way, how far out do I have to go?
10.
Yeah, 10 it looks like, right? Looking at this formula, it looks like if I go out 10, wait, that's not right.
Yeah.
That's not dumb.
Let's just use n.
Okay.
Let's just let n be 10. So 10 is the number that describes how far out I have to go in order for this to be true. Okay? However, what if she had challenged me with something more dramatic, like the next possible smallest number you could think of, 1/100th. If she I'm not going to redraw the picture, but if she challenges me with 1/100th, now she's making a further demand on me. She's demanding that I get really, really, really close to 3. Now, how far out do I have to go in order to meet that demand?
N equals 100.
1, I have to go out to n equals 100. Okay, so we can play this game all day where she keeps challenging me and I keep meeting the challenge and she challenges me again and I meet the challenge again. But ultimately, I'm going to win, always, right? So eventually, I demand a reckoning by algebra and I just say, all right, look, I'm tired of this meeting your endless demands. Just give me any number, epsilon, which just represents the smallest possible number you can come up with. And what should my automatic retort be to any tiny number that she gives me?
1 over epsilon.
1 over that number. That works for this particular sequence at least. That if she gives me some tiny, tiny, tiny number, based on your intuition about this particular formula, if I take the reciprocal of that number, that describes how far out I must go such that beyond that number, all the terms of my sequence will be within. Okay.
Prove that beyond that.
Oh, that's what we're going to do this in a minute. Now I will just give you the. When does this period end? What's that thing say?
No one like one this.
What does that say? 38? Like crap. Okay, so here we go. Let's just do this. Should we do one more? Let's do one more. So suppose I ask you for the limit as n approaches infinity of 2 minus 1 over n squared. What do you think this is?
2.
Are you moving the camera to keep up with all this? What is this? Yeah, I think this is 2. And now, okay, I'm too lazy to draw a picture well, so I'll just do a crappy one. 2, 3. We think that this is 2. When I plug in 1, I get like 1, right? When I plug in 2, I get, I get 2 minus a 4th. When I plug in 3, I get 2 minus a 9th. When I plug in 4, I get 2 minus a 16th, so it does appear to be getting closer to 2. Okay, now, if she challenges me with some epsilon of like 1/10th, how far out do I have to go in order for that to be true? How about we pick a better one? How about if she challenged me with an epsilon of 1/100th? Now how far out do I have to go?
10.
Does everyone see that? This is functions, right? So okay, I'll assume you just get it. Yeah, I have to go out to 10, because when I'm out to 10, then 10 squares, and then it works out, right? And if she gives me like 1/10,000, how far out do I have to go in order to meet her demands?
100.
Now 100. So what appears to be the secret formula now?
Square root.
What appears now? If she gives me a tiny number epsilon, how far out do I have to go?
Square root.
1 over the square root of that number will be sufficient. Okay, so let's now do this. I think we are now mentally we are prepared now for the full actual definition, and here is the full actual definition.
Of what?
It goes like this. Take any sequence whatsoever, so take the limit as n goes to infinity of that sequence. And let's suppose that we say that limit is L. What we have just been kind of discussing is what should be the formal definition of what precisely we mean when we say that a sequence has a limit L. And, well, we think of it as being some number that the terms of the sequence are getting closer and closer to, perhaps sometimes above and sometimes below, etc. And the terms can do whatever you want for a while, right? They can spend a million years doing random stupid crap. All that matters is what happens at the end. And at the end, they better be getting arbitrarily close to L. And what we mean by getting arbitrarily close to L is that should anyone at all make some kind of demand, and that demand comes in the form of a number, a tiny number epsilon, for any tiny number epsilon challenge, I should be able to go out far enough, and we call this number big N. Big N is the number to which out I must go, such that beyond big N, all the terms of my sequence are between L minus epsilon and L plus epsilon. Does this make sense? Okay, so I can give you this definition formally in terms of quantifiers. The limit as n goes to infinity, the base limit is L, if and only if. Someone want to do it for me? What should the first thing would be?
For any arbitrarily chosen epsilon.
Yes, for any arbitrarily chosen epsilon, where I insist, however, that epsilon is a positive number. For any tiny positive number whatsoever, what claim do I make?
There exists n.
That there exists a big N, also a positive number. And what should be true about that number, big N?
For all n, a sub
For all little n,
little n for a sub n.
No, n is greater than
And n is greater than
if n is, we do greater than, if n is greater than big N, then
a sub n is a sub n minus L is.
yes, then a sub n must be somewhere between L minus epsilon and L plus epsilon. Does this capture what we've been talking about? For any epsilon, no matter how much of a challenge she gives me, there is some kind of n. Now, and the n is going to depend on the epsilon, right? Because the smaller she squeezes me, the farther out I might have to go. But there exists some number n such that for any terms beyond that number, then the terms of my sequence always lies between boom, boom, boom. Who's that question?
No, never mind.
Okay, good. And as someone was mumbling, you could rewrite this instead as that the absolute value of L minus a sub n. Can you do it like that? No, you usually do it like this. A sub n and L is less than epsilon. This is the same thing, right? The distance between the term and the limit is less than any number whatsoever that you might come up with. Who's up?
Shouldn't it be less than or equal to?
No, we do it this way, just because. Okay, let's do a proof. Jamie was like, all right, but how do you actually prove that? You prove it by actually proving it. So let's do it for a particular problem before the bell rings. What?
How tiny does epsilon have to be?
It can be any number. It can be any positive number whatsoever.
So like you can't have, so it can't do anything at the start then?
Yeah.
Like you can't go like,
No, but all I have to do is go out far enough such that it's true.
You could just choose like a
Okay.
billion every time.
oh, okay.
Yeah, you could just, yeah. And in fact, if a particular big N works, then any larger big N will also work.
Yeah.
Okay, this doesn't take that long. Let's do, shall we do, here, we'll do, I gotta go over for you right here. Let's do the limit as N approaches infinity of 2 plus -1 to the N over N squared. Okay, this is a good problem. It basically does everything. Let's change it to a 3 for more fun. Okay, so here's the limit. First of all, what is the answer? 3. And now we are going to prove that this is true. Okay, in order to prove this, I need to okay, let's write out. What is it that actually needs to be proven?
For all.
For all epsilon greater than 0.
And there exists.
Kind of regurgitating the definition back to me. There exists an N greater than 0 such that
For all.
for all little n,
If n.
little n is greater than that number big N, then the distance between the nth term and 3 is less than epsilon. And again, the picture looks something like this. 1, 2, 3, 4. That's probably good enough. Here's 3. When I plug in 1, it's like 4, right? Is that right? If it's 1, right?
No, it should be.
Isn't it? Yeah.
No, it should be.
When I plug in 1, it's. Oh, no, sorry.
Yeah,
It's
you
2.
get 2.
When I plug in 1, it's 2. When I plug in 2, it's 3 plus a fourth. When I plug in 3, it's 3 minus a ninth, etc. So these are going to bounce on either side of 3, but it seems like it's working out. And what I have to do is, given some kind of epsilon challenge, so that number is 3 plus epsilon, that number is 3 minus epsilon, I need to go out far enough to some number big N such that beyond big N this is true. Okay, well, I have to prove this somehow. How is this proof going to occur? Well, this proof is going to occur by, someone's going to give me an epsilon. I'm going to have to respond with a big N, and then I'm going to have to prove this conditional. And proving this conditional is going to involve assuming this and then deriving this. Right? So the heart of the proof is going to be proving this fact. All right. So what we do is we work backwards. So we do this thing called a discovery phase. In a discovery phase, you work backwards. So you just say, all right, suppose a sub n minus 3 is less than epsilon.
Wait, what?
We work backwards. Let's discover. This is not the proof. That's important. This is not the proof. This is just scrap paper.
This is the discovery.
I'm not stalling. Discovery phase means that we're just screwing around. Okay, so we're just scribbling some crap, and then the actual proof is going to come later. Okay, so what we are going to do is, the question we're basically answering is, I wonder for which ends this is true. I'm sorry, I'm going to finish this quick and let you guys go. For what ends is this true? So, yeah, what is a sub n? Well, it's that, right? So I'm wondering when is 3 plus -1 to the n over n squared minus 3? I wonder when that is less than epsilon. Anyone have an idea?
You subtract.
Okay, the 3's cancel. So I really need to answer the question, I wonder when this is true.
Well, you could like
Oh, then you just kind of do the thing.
No, wait, not yet.
absolute value rules.
Yeah, this -1 to the n is like just a bunch of stupid -1s, right? Or not. So that's just like irrelevant. The absolute value kills them all.
Yeah.
So this is really just 1 over n squared is less than epsilon. Do you agree? Okay, so I'm still answering the question, for what ends is this true? Okay, well, what can I do now?
Multiply by n squared and divide by epsilon.
Yeah, or you could just like reciprocate.
Yeah.
When you reciprocate, it like flips the sign, right? Did we talk about that?
Yeah.
Oh, yeah.
Reciprocate, flip the sign, and then finally, take the square root. And so what I have just discovered is, okay, and also all these steps are reversible, right? Nothing I did, since all these steps are reversible, I started with the thing I was trying to prove, and then I deduced that n is greater than 1 over root epsilon, which is another way of saying, if n is greater than 1 over root epsilon, then the proof will work. So this suggests, what should I set big N equal to? 1 over root epsilon. Okay, half the proof is now completed. Actually, the proof is 0% completed, but half the work is completed. And what we did is we discovered the secret relationship between big N and epsilon. Okay, now we do the actual proof. We can do this in 1 minute. How does the actual proof work?
Hey, could you move to the bit? Yo.
How does the actual proof work? What's the first thing that happens? I'm really sorry, guys. I'm going to look for a second. What's the first thing that would happen if you were trying to do this proof? Someone would suggest an epsilon. Yes, you are right. So take an arbitrary epsilon. Take an arbitrary epsilon greater than 0. What do we do? So imagine that someone has just shouted out an epsilon. What do we do? Yes, we immediately respond with a retort of, haha, 1 over the square root of that number that you just challenged me with. Okay? Having established that big N, then what's left to prove? What's left to prove is that conditional. Right? So now we just go about proving that conditional. How do you prove a conditional? Assume the antecedent derives the consequent. So assume that N is greater than big N. Now what?
Plug it in.
So N must be greater than 1 over root epsilon. Now what?
You just said
Square both sides. Yeah, you basically just reverse all the steps. But that was just scrap paper. So that's why, but it's inspiration for us. So square both sides, then reciprocate. Then rewrite 1 over n squared in some kind of awkward form, which is, however, totally legitimate. Because it just is. Because that just is that, right? So it's allowed. It's legit. You might laugh, but it is totally legit. Now what?
add 3, subtract 3.
Add 3, subtract 3. And indeed, I have just proven rigorously that the distance between the nth term of my sequence and the number which I claim to be the limit is less than any number which possibly you challenge me with. Okay, so that is how you prove. That is how you prove that a sequence has a limit. Okay, man, should I give you guys for homework? All right. That lesson
we try to do
went
homework or not?
over. Let's do.
Wait, should we turn it over?
Yeah, I'll let you guys figure this out. Everyone, take one of these. Take one of each of these two.
Hey, I'll put the camera on this.
Yeah, turn the. What are you doing? Oh, on this.
Ah, never mind.
Grabbing.
It's not as
Can I have the
technical.
homework for today? Right here. And can I stupid square problem? We lost 5 minutes. Can I? Oh, that's coming later. Before you understand it for the sums, you have to understand it for the sequences. Yeah.
How can you? It's a philosophy problem, not doing it.
What to do?
Still recording.
Good. I just have like no time until after work. Can I do that after work?
How this one?
What if I fax it? So, yeah. Okay, so I'm gonna do it.
For what? What's she doing?
I don't know. You know me, I'm the 28.
Second
I'll
for
just like
my
it. I figured out what you were saying.
I thought there was some.
Can you like turn this off?
Just get my feet work.
Stop, did you turn it off? Is it still recording? Okay. Okay, bye David Miller. Anyone have anything to say to David Miller or
You missed learning calculus.
Jesse? Okay, bye guys.